Good afternoon, everyone.
Good afternoon.
Afternoon.
Oops, no one waters that. Here's the link to follow everywhere. We'll have a short daily quiz today. We're going to see we are missing Chevy and Amari. But it's 1:59. They got a second. All right, well, it's 2 o'clock. I'm not going to waste y'all's time. So hopefully, here we go. There's Nabari. So hopefully Chevy will come in at the last, or here in a minute or two. But you now have a quiz. And that daily quiz is asking you if the three vectors that you see here, 1, 1, 2, 2, 2, 4, -1, -1, -2, are these vectors linearly independent? Okay. I'm giving you all a nice little choice, simple choice of yes or no. We'll be asking, it won't go towards your grade, but I'm going to ask you for your reason. So make sure that whatever conclusion you come to, you have a reason for it. I'm just going to give you all until 2:03, which is just 2 more minutes, just under 2 minutes from now. So are these vectors linearly independent? You got 1 more minute. Got 1 more minute. Make sure you open up that quiz, Chevy. All right, 30 seconds. 30 seconds. All right, we got everyone's responses in, but I'll give you all a gist to the end of that. So 10 seconds. Make sure you think about it. Make sure you know your answer and you can justify it. I'm gonna lock them here in 5, 3, 2, 1. Locking answers now. All right, most of y'all did get it correct, but I want to hear your justifications. I'm going to call on just 2 people. I'm going to ask for 2 people to give their reasoning. Let's see. I want to pick on Josh. Josh, do you mind telling us what you answered and why? As best you can.
All right. I chose the option no, and the reason why I chose no was because I just assume that the determinant is not zero. I just assumed that wasn't gonna be zero. Just a guess.
All right. Thank you for being honest. All right. And then let's see. Nabari, what did you answer and why?
I answered no because the vectors themselves were multiples of each other. So they could be the C would be they could be real numbers instead of zero.
Perfect. Absolutely perfect. So yeah, the correct answer here is no, these are not linearly independent. They are literally dependent. And just like Nabari said, if you just look at the vectors, so Josh, your whole process of saying put them into a matrix and calculating the determinant, still 100% correct, right? That is a way that you could come to concluding that these are linearly dependent. You get that the determinant of this matrix would be 0. Okay? But if you look at just between those first two vectors, the second vector right here, the 2, 2, 4, is just 2 times the first vector. So that 1, 1, 2. So just by knowing that, I could say let C1, I don't know, be 2, C2 be -1, and C3 be 0. I plug that into my equation up there, and I'll end up getting that left-hand sum will end up being equal to all zeros. I could also do something similar with C1 and C3 because between these two matrices right here, it's just multiplied by a -1. Okay. So these are not linearly independent, and what that always implies, if you're considering linear dependence, and something that you see in the homework, if a set of vectors is linearly dependent, this will always imply that at least one of those vectors is a linear combination of the other vectors.
I don't really understand the concept of linear combination.
Linear combination, constant plus vector, plus another constant, plus another vector.
So what does it mean if one vector is a linear combination of the rest?
That means it can be taken as the sum of all the other vectors. So just like 3 is a linear combination of 1 and 2. I could also say the vector 3, 2, 1 is a linear combination of 3 times 1, 0, 0, plus 2 times 0, 1, 0. Crap, I ran out of room. What's supposed to go right here is plus a 1 times 0, 0, 1. So the vector 3, 2, 1 can be written as a linear combination by a constant multiple and a sum of different vectors. That's what it means to be a linear combination. So let me finish that sentence. This implies at least one of those vectors is a linear combination of the other vectors. And whenever you're thinking about that definition as well, Eliam, for linear independence or dependence, what you're saying is the linear combination of those vectors can only equal 0 if your coefficients are 0. And if you look back at that definition, it's because we're taking just some combination of adding vectors together and multiplying those vectors by constants. That is a linear combination. Oh, my back's bothering me. Does that make a little bit more sense? We're going to be dealing with linear combinations more today.
Yeah.
All right. So let's get back. So actually, that leads perfectly into next thing I wanted to talk about, which is called spans. But quick question: any questions on daily quiz or any of this right here? All right, I'm not hearing anything. So let's move on. So next thing we're going to define is the span. And then once we have linear independence and once we have this idea of span solidified, then we're going to define what are called bases or basis. So let's just V1, V2, all the way to some Vn. So we have some collection of vectors. It would be vectors of a vector space V. And use a nice big old capital V forward just to represent the vector space. The span of these vectors, V1, V2, all the way to Vn, this is a set. And it's just the set of all vectors of the form just what we were talking about, that linear combination, C1, V1 plus C2, V2. i.e., it's the set of all vectors that are linear combination of those four. Or n vectors, sorry, I don't know why I said four. All vectors that are a linear combination of V1, V2, Vn. Really, it's just saying another way to think of it, if I'm giving these certain vectors, what can I create with these vectors? What are all the different vectors that I can create just from these building blocks, just from this finite number? So I'll give you all a second to write that down, finish writing that down, just 10 seconds. Give me a thumbs up if you're done. We're going to do a quick example. Thank you, Nabari. Thank you, Khalid. I am cool. So I'll give you all just 5 more seconds since most everyone's got it down so we can make sure we're still moving along. And sadly, we don't have this nice big old whiteboard where you can just kind of keep track as we're going through. I got this nice little small space to work with. All right, so let's get an idea of spans. All right, so is the vector 1, 2, 3 in the span of the 3 vectors 1, 1, 1, 1, 1, 0, 1, 0, 0. And another way to state this question is, can I use these vectors 1, 1, 1, 1, 1, 0, 1, 0, 0, add them together in a particular way so that I can get this vector 1, 2, and 3. So if it's in this span, that means it needs to be a linear combination of these 3 vectors, which means then that 1, 2, 3 should be equal to some constant times that first vector plus another constant times the second vector plus another constant times that third vector. So 1, 2, 3 should be a linear combination of those three vectors. And if it is in that set, then I should be able to find those coefficients at C1, C2, C3. If it's not in that set, I'll come to some logical conclusion that says it can't happen, right? I.e. a contradiction. I shouldn't say logical conclusion. I'll come to a logical contradiction. They'll say that it's not possible to choose a C1, a C2, or a C3. Okay? But similar to how we're dealing with linear independence, we just do this the same way. Combine one of those sides into a single vector. And I'm going to get from that a system of equations. Oops, not plus. So if I multiply those constants through that C1, C2, and C3 and add all those vectors together, I'm going to get the vector C1 plus C2 plus C3. That's going to be in the first row. And I'll have that C1 plus C2 in the second row. In that last row, I'll just have a C1. And again, similar to kind of what we saw on Tuesday, this gives me a system of equations that I can work with. First one tells me that C1 plus C2 plus C3 has got to be equal to 1. Second one tells me that C1 plus C2 has got to be equal to 2. And the last one tells me that C1 has got to be equal to 3. Now, if I wanted to, I could take this system, turn it into a coefficient matrix, an augmented matrix as well, and solve. But I don't need to, because just looking at the system, what is one coefficient that I already know value it, or what the value is?
That C1 is already equal to 3.
Yeah, so I know C1's got to be equal to 3. So I'm going to try to write it in blue just to make sure that we're seeing that this is the important information. C1's got to be equal to 3. Well, then once I know C1, what do I immediately also get?
C2.
C2,
Yeah, I know what C2 has got to be. What's C2 got to be?
-1.
Yeah, -1. And then once I realize that, that also gives me what C3 has to be, which is also 1. Oops, I think you tried to unmute yourself and mute yourself very quickly. I didn't get to hear you. But I'll go ahead and shortcut it. It's -1 as well. So as long as I use these specific constants, 3, -1, -1, I can use those constants in these three vectors, the 1, 1, 1, 1, 1, 0, 1, 0, 0, to end up creating this vector right here, 1, 2, 3. And if we wrote it out fully, it'd be 1, 2, 3 is equal to 3 times 1, 1, 1 plus -1 times 1, 1, 0 plus -1 times 1, 0, 0. This is what spanning sets. What can I create from the linear combination of these? And there's many, many, many more vectors that I could create from these three vectors, 1, 1, 1, 1, 1, 0, 1, 0, 0. Actually, an infinite amount of things, but we'll see why that's here, the case here in a second. But anyone got a question about span?
So the span of this whole thing is what?
We'll show that it's R3.
Huh?
We will show that it is R3, the Euclidean space, R3.
So the span is R3, is not 3, -1, and -1?
No. The span, remember the span is the set of all vectors that you can create from linear combinations of these vectors.
So the span is 1, 1, 1, 1, 1, 0, and 1, 1, 0, 0?
No. That is the vectors that you use to create the span.
So which one is the span?
It's R3. So it's all vectors. Again, we'll see why. Just be a little patient with me. But I'm just asking in this question, is this vector in that span? Because that span for that specific problem, if we're still using that set of vectors, so I would say X isn't in that span of 1, 1, 1, 1, 1, 0, 1, 0, 0. If X is equal to some constant times 1, 1, 1 plus another constant times 1, 1, 0 plus another constant times 1, 0, 0. So anything that can be written as a linear combination of those three vectors is in that span. And there's not just a finite set of things. There's a lot of things that can be in there. Use that vector notation. Make sure you're thinking of these as vectors. Okay, more questions. And if not, give me the thumbs up so I get that cue, visual cue that we can move on. Allium, keep asking questions if you got them.
So if you was to ask me what's the span of this, what would I answer? Just R3?
It'll be R3. You haven't gotten the tools yet to say why. I'm giving you the tools yet. And usually you don't ask the question, what is the span of the set? You just know that it's got to be linear combinations of these things because it's always hard to picture. And that's also why I never asked you, right? What is the span of that set? I just asked you, is this thing in that span? Because the question that you're asking is a very, very hard question to answer until we learn about bases or bases. Mm-hmm.
Yeah, 'cause I know for bases we have to satisfy two things.
Mm-hmm. Yep. So let's use that and let's define it. So what is a basis? Well, definition. The vectors v1, v2, all the way to vn form a basis for a vector space or for the vector space V if and only if. Whoa, why'd that go green? As Eliam said, we got two things that we have to satisfy. First thing is that these vectors are all linearly independent. Let me write it down here. That is the first thing that these set of vectors have to satisfy. And then what is the second thing? This is what makes basis unique as a definition. So what was that second thing, Eliam? Do you remember?
They have to span, something like that.
Mm-hmm. Yep, your vector space is spanned by these vectors. So the span of V1, V2, all the way to Vn, that set is just your vector space. What this last thing, what 2 is telling you, any vector in that space is a linear combination of those vectors, v1, v2, all the way to vn. And that's important because then what we're saying is if we have a basis, we know what our building blocks are for this vector space V, right? Think like R2 or R3, vector spaces that we're kind of a little bit more comfortable with now. They have building blocks. They have specific vectors that I can just add, subtract, and multiply by and create any other vector in that space. That is what bases are. And they're literally independent and they span our space.
I have a question, Professor.
Go for it.
Looking at the previous problem, the vector space would be v1, v2, and v3.
No, so the vector space is the space that you're working in. It would be, if you're trying to relate to the notation, this would be the vectors that we're considering.
Mm-hmm.
V2 and v3.
And which one would be the vector space?
Vector space that you'd be working in is R3 because we're considering vectors with 3 elements. And all those entries in those vectors are real numbers. All right, back to the definition just so some of y'all can finish writing it down. While you're finished writing it down, so first off, give me a thumbs up if you're done. Second off, ask any more questions. Don't let Eliam dominate. I know some of y'all have to have questions as well. So Eliam, if you still have questions, keep asking.
Okay. I'll just let my classmates ask questions, and if they don't ask, then I'll ask something.
Now, I love that you're active. Just want to make sure everyone else is speaking up if they've got them. I think I just saw a bunch of thumbs up. So just some quick examples of basis, or of a basis. So consider the vector space R4, for example. Okay. What do elements of R4 look like? Well, they're vectors, and each vector has how many real numbers in it?
4.
4. So, you know, examples like 1, 2, 3, 4. -5, 100, pi e. Right, this is what elements of R4 look like. In R4, we know of a basis. We can think of a basis for R4 without having to be too creative. And it's the following collection of vectors. So I just have these 4 vectors, right? Where I have a 1 in the first position, 0 is everywhere else. The next vector is a 1 in the second position, 0 is everywhere else. A 1 in the third position, 0 is everywhere else. And a 1 in the fourth position, and 0 is everywhere else. And it's pretty easy to see that just from looking at these 4 vectors, they're linearly independent because where there's a 1 in each vector, there's zeros elsewhere. So if I look in that first row, this first vector will only ever create anything from that first, or for that first element in any vector. The second vector here will only ever create something in the second position, and so on. These are linearly independent, and if I ever wanted to create a vector, let's say 5, 6, -1, 2, well, it's relatively easy to see the linear combination of these 4 vectors that will make that work. I take a 5 times the first vector, so 1, 0, 0, 0. Add it to a 6 times the second vector, 0, 1, 0, 0. I'm going to add to it a -1 times the third vector, and then a 2 times the last vector. So this is an example of a basis in Rn. I can kind of fill in. What was that, Chevy?
I have a question. So how did we get the 5? That's a 6?
Mhm.
-1 and 2. How did we get that?
What are my entries here in this vector that I'm trying to recreate?
Oh, so that's just your what?
So I just said take a random vector from R4. I said let's
Oh,
just let this random vector be 5, 6, -1, 2, for example.
okay,
I'm not
okay.
trying to do a general case. I'm just trying to say, here's why it's easy to see. And all I have to do with these 4 vectors, whatever my first element is in the vector I want to create, I just take it, multiply that entry by my first vector. Because that first vector is the only thing that's going to generate anything for that first row. Because everywhere else, I have zeros. Okay, similar for the 6, similar for the -1, and similar for the 2. Okay, so this has a basis. It's not the only basis, though, for R4. Another basis would be the following: 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0.
So this is another basis it has.
Yeah. So these 4 vectors right here would also be a basis for R4. And this is something that we're actually going to prove. Because it's not as straightforward from just seeing these things, these 4 vectors. When we look at the first set of vectors up here, we can claim it's a little bit more obvious to see up front, but not so much here. We want to actually show that these are linearly independent, and that if I take anything from R4, any vector from R4, then I can write it as a linear combination of these 4 vectors down here. So always to show things a basis, show it's linearly independent, show that it spans your vector space. Take any element of your vector space and show that you can write it as a linear combination of these vectors.
So the one on the bottom,
Sorry?
the
Hold
one,
on.
the one on the bottom that you circle, that one, it would also be linear independence.
We're going to show it.
Okay.
So we're going to show that it's linearly independent and that it also spans R4. That I can take any
I have
vector
a
with
question.
4 real numbers and show it's a linear combination of these 4 things. What's up, Eliam?
When I was watching the videos that you posted for basis, the guy, he had a matrix. He had like vectors, and he made them into one matrix, and they were like real numbers, so like a lot of numbers. When he did the reduction, the row reduction, even though the matrix was not was dependent, he took the pivots from the matrix after he reduced it, and then he said that the pivots were independent. So the matrix was dependent, but the pivots were independent. That's confusing.
I don't remember that at all. So how about when we have that office hour meeting this afternoon, we look at that together?
Okay.
'Cause I don't remember that.
Okay.
So let's just go ahead and prove this example. Okay, so first thing we want to show is linear independence. Right, and we have that our vectors C1 times 1, 0, 0, 0 plus C2 times 1, 1, 0, 0 plus C3 1, 1, 1, 0 plus C4 times 1, 1, 1, 1. This has got to be equal to my 0 vector in R4, which is just a vector with 4 elements, and all 4 of those elements are 0. And we'd be able to turn this into a system of equations pretty quickly by adding all that left-hand side together and then looking at each row and seeing what these things are equal to. So we'd get C1 plus C2 plus C3 plus C4 has got to be equal to 0. We'd get C2 plus C3 plus C4 has got to be equal to 0. C3 plus C4 has got to be equal to 0. And C4 has got to be equal to 0. So again, here we have 2 different ways we can approach this. One is by looking just at the system that we have and make conclusions on what C1, C2, C3, and C4 have to be. And if you did that, well, the first thing you see is that C4 has got to be 0. If C4 is 0, then C3 is 0. If C3 and C4 is 0, then C2 has to be 0. And then if you look at that first equation, if C2, C3, and C4 have to be 0 for that equation to be true, C1 also has to be equal to 0. The other way you could do it is what we talked about on Tuesday, which is by throwing each one of those vectors into a matrix. And it creates the columns for that matrix. Right, which is also just the coefficient matrix for that system. And we said, okay, if I calculate the determinant of that matrix, if it's non-zero, then they're linearly independent. What is the determinant of that matrix going to be?
1?
1.
Yeah, it's going to be 1. Because I can go back and say, oh, hey, yeah, remember we said we can calculate determinants nice and easily if it's an upper triangular matrix. So look at my diagonal. I've got 1 or zeros all below my diagonal, which means the determinant of that matrix is just the product of the diagonal. So it's 1 times 1 times 1 times 1, meaning that the determinant of this matrix is 1. So either way you look at it, whether you look at it from the system or from that matrix theory that we've built up over the semester, either way, our conclusion, just to kind of fit it down there in the right-hand corner, they are linearly independent.
So if the determinant is 0, okay, I'm confused.
The determinant is 0, then we know it's linearly what?
Dependent?
Dependent. That was that theorem that we established at the very end of class on Tuesday. All right, so we now have this set collection of vectors is linearly independent. Last thing we have to show is that the span of those vectors, so 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0. Whoops, I'm trying to write too small. Go away. 1, 1, 0. And 1, 1, 1, 1. That this is equal to R4. That using these 4 vectors, I can create anything that is in R4. So just let X, Y, Z, and W be real numbers. Then I know that the vector using those entries, so X, Y, Z, and W, that is a vector in R4. And the reason why I want to use variables for each one of those entries is this way I'm not nailing down what the first entry is, what the second entry is, and third entry and fourth entry. I'm keeping it general. So saying you fill in, you tell me what X is in any case, I'm going to be able to tell you what vectors, what combination of these 4 vectors I'll need to use to generate that value in the first entry. Same thing for the second entry, third entry, and fourth entry. So that's what we're going to have to do. So I'm going to have to figure out, what does C1 have to be? I multiply it by 1, 0, 0, 0. What does C2 have to be for multiplying it by 1, 1, 0, 0? And C3, 1, 1, 1, 0. And C4, 1, 1, 1, 1. Right? Can I write, even in any case, no matter what you tell me X, Y, Z, and W are, can I tell you what C1, C2, C3, and C4 need to be to make that linear combination happen? Okay, well, again, it's a similar process, right? But instead of solving for zeros, I'm now just solving for some unknown values. But I'm still doing the same process. So I'll combine that linear combination into a single vector, giving me X, Y, Z, and W is got to be equal to C1 plus C2 plus C3 plus C4. Then I'll have C2 plus C3 plus C4. And I'll have C3 plus C4, and then C4.
Sorry.
Oh, you good? So again, this turns into a system, right? For these 2 vectors to be equal, each corresponding entry has to be equal, which means I need C1 plus C2 plus C3 plus C4 needs to be equal to whatever X is. Then I need C2 plus C3 plus C4 to be equal to whatever Y is. And I also need C3 plus C4 to be equal to Z, and C4 equal to W. And even though I don't have an exact number for X, Y, Z, and W, I still could turn this into an augmented matrix, or reduce the augmented matrix, and that would tell me what the solutions for what C1 needs to be, C2, C3, and C4. But I have a nice little form for this system, and I already know what one of those values has to be. So what constant, C1, C2, C3, or C4 do I already know right off the bat?
C4.
Yeah, I already know what C4 has to be. C4 needs to be whatever that last element is in this vector that I'm trying to recreate. So C4 needs to be equal to W, whatever that is. But then I can use that information up here into that second one. So if I replace C4 with W, that leaves me with C3 plus W has got to be equal to Z, which then tells me C3 is equal to what?
Negative C4 plus C.
So it wouldn't be plus C, and I've already replaced C4 with W.
Wouldn't it be C3 equals Z minus W?
Yeah.
Wait, isn't that the same thing?
So you said Z plus C4. So I heard a plus.
No, I said C4 minus Z. Which is the same thing as Z minus C4.
No, because so you just said C4 minus Z is the same thing as Z minus C4. Subtraction is not a commutative operation. It does matter what order that we subtract things in. Just like how 2 minus 1 is not the same thing as 1 minus 2. right. So now we've got two known values. I'm going to write it here in green to the right. Try to keep us all on the same board. C4 has got to be equal to W. We also now have C3 is equal to Z minus W. So now that I have C3 and C4, what else can I solve for?
C2.
Yeah, C2. So I'm just going to try to write in this same little space. So I had C2 plus C3, which is Z minus W. And I'm going to have plus a C4, which is plus a Z. That's got to be equal to Y. And again, my goal is to solve for that C2. Subscript's not really wanting to show up there. I can at least simplify a little bit what I see there. So it'd be C2 plus 2Z minus W is equal to Y, which tells me C2 is equal to what? Chevy, I'm going to pick on you. I solve for C2 here. So that equation down there means I've got to move everything else to the right-hand side, which means on that right-hand side, I'll have what?
Okay, for some reason, I can't see the bottom of my screen.
Well, how about Leanna? How about you help her out?
I see it, I see it. Okay.
I was gonna say it what C2 would equal 2Z minus W.
Say that one more time.
C2. Oh, okay. C2 would equal 2Z minus W plus Y.
That's why, yeah. Or
Plus Y. So I need to move this over, right? Move the 2Z and the minus W over, which means I have to subtract a 2Z. I got to add a W.
Right.
I'll be
So
left
it
with
would
a
be
Y.
negative. Yeah.
Yeah, you could start with a negative 2Z if you wanted to. As
Okay.
well. Yeah, but essentially you should have a Y minus a 2Z plus a W, or if you rearrange that, some making sure that you're keeping track of that negative 2Z. That is absolutely correct. So let's see if I can fit this in here. C2 is then got to be equal to Y minus 2Z plus W.
I have a question.
Mhm.
So I'm a little confused here. So you have C3 is what we found, Z minus W. And then for C4, wouldn't we replace it with W instead of Z?
Yeah, I don't know why I have a Z there. I'll explain why y'all ladies got something different, why I have something different in my lecture notes. Good catch, Josh. You should be confused. Dang, 248. All right, so it'd be plus W, which means C2, simplify that left-hand side for me then, Josh, since you're correcting us.
So it will be, I think the W's will cancel out, right?
Yeah, W should cancel out.
All right, so then it will just be C2 plus 2 equals Y. So then it will be C2 is equals to Y minus 2.
So it's a Z, but yeah.
Oh, Z. Oh, my bad. Okay.
That's why I draw a dash over mine to try to differentiate between Z's
I
and
keep
T's.
hearing two and I getting confused, like where the two coming from.
All right. Well, I don't know why. Wait, why am I writing Z again? Oh, yeah. Z's there.
Oh gosh, man. No, man. Think confusing. We take a break, take a week break.
I wish we
Yeah,
could.
yeah.
Sadly, we don't. But we only have 5 weeks left. That month is going to fly by before you know it. So C2 is just got to be equal to Y minus Z. And then since we're running out of time, let's quickly get that, figure out what C1's got to be. And Josh, I'm depending on you again to make sure I don't screw up. So everything is on you. If I'm correct, I get all the glory. If I'm wrong, you get all the credit. So C1 plus C2 plus C3 plus C4 has got to be equal to X. And I know what C2, C3, and C4 are going to be. So this is C1 plus Y minus Z plus Z minus W plus W's got to be equal to X. So again, I have some things cancel out. What cancels out here?
The Z
Yeah, the Z's would cancel each other out. What
and the
else?
W.
Yeah, the W's, leaving me with C1. I know I'm writing down at the very bottom, but C1 plus Y is equal to X. So C1's got to be equal to what?
X minus Y.
Yeah, X minus Y. But now what this tells me is you give me any value for X, Y, Z, and W. This is the combination that I need to use for each of these coefficients, C1, C2, C3, and C4, that I can use these 4 vectors to create that. So here, what we've shown, let's try to sum it up on the next page. So since any vector X, Y, Z, and W, whoops, and that's Z, not a 2, which is in R4, can be written as a linear combination C1, 1, 0, 0, 0, plus C2, 1, 1, 0, 0, plus C3, 1, 1, 1, 0, plus C4. So again, that linear combination that we were talking about. So that's in the span where C1 was what again? Let's see, X minus Y. C2 was going to be Y minus Z. C3 is going to have to be Z minus W, and C4 would be whatever W is. So I challenge you, because I wanted to do it before we had to leave, but 250 is already come and passed. But fill in values for X, Y, and Z, and W. So someone give me a value for X.
1.
Right. Someone give me a value for Y.
3.
3. Someone give me a value for Z.
58.
58. Yay, we're getting crazy. And one more. And
No man, never mind.
No.
Not 58, because we don't have time. Not 58.
Too late.
7.
The next one could be 12.
12. All
It's
right.
got 58. Use 1 again.
So 1, 3, 58, and 12. I now know if I just kind of associate with this as each of these has X, Y, Z, and W, and I fill in the appropriate values for C1, C2, C3, and C4, you're going to see that right-hand side, when I add it up all together, is going to be equal to 1, 3, 58, and 12. Because as long as we choose those constants to be these specific combinations, we'll always be able to generate whatever vector in R4 that you give. Thus, we get to come to that conclusion that this set, I'm going to have to go to a new screen, and I'll come back if you want to look at this. Thus, this set of vectors, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, and 1, 1, 1, 1. That collection is a basis. Or R4. This is what we were trying to prove. So I'm going to go back to that last screen where we were talking about where we defined C1, C2, C3, C4 here in a second. No, I'm already over time. So if you need to go, you are more than welcome to go. If you have questions, you're welcome to stick around and ask questions. Otherwise, I will see y'all on Tuesday.
I mean, what are you gonna say next?
Hmm?
What are you gonna explain next?
You mean on Tuesday?
No, like today. If we don't leave, what will you explain?
No, I'm not explaining anything else. I'm just, if you got questions, you're more than willing to say.
Okay.
All right, all right.
You see, that's why people were
I'm
staying.
not going to say go ahead and leave, and then I'm going to, explain the life, the universe, and the meaning of happiness. No.
Yeah, I think that's why people stay, because you look like you about to explain something.
Yeah.
No. Maybe if someone asks an interesting question, yeah, but we might accidentally stumble upon something. But nah, it's just questions for y'all.
Yeah.
Hmm.
I do have a question before I leave
Okay.
in regards to the homework, not the web work, but the book
Okay.
homework. So, for 3.3, we have to do number 1 BC,
Yep.
number 2 BC, and number 4 AB.
Yes.
So based on that, we have to answer 3.4 questions 2. That's the only one that relies on 3.3 to be answered, right?
Mhm.
So for my, let's say for my 3.3, the first one, for A and B, for B and C, they're both dependent. So in 3.4, number 2 is asking, indicate whether the given vector is a basis for R3. So it's not, because it's linearly dependent. Just by that, I know it's not a basis of R3.
Okay. Is that
Right?
your question?
Yes.
Because it sounded like you just gave me a conclusion.
My question is, if they were linearly independent, which of the steps we did today would I have to do to figure out if it's a basis?
Well, what are the two things you have to show for a set to be a basis?
If it spans. If it's linearly independent, that's one. But if it spans.
Yep.
So the spanning was what we just did, like literally what we were just laughing about.
Yep. Right. So we went through a process. Started off with, can I take anything in R4, which was the vector space I'm living in right now? And can I take it and write it as a linear combination of these 4 vectors that were given?
Mm-hmm. So, okay, all right. So let's look at 3.4, number 4. They give us 3 different vectors, but they don't give us what they equal to, as in they don't give us x1, x2, and x3 equals 0, 0, 0. They just give you 3 vectors.
So number 4, yeah.
We would equal them to x, y, and z, and just figure out how we could get x, y, and z from the vectors given.
Yep.
Okay. All right. That's my question, Professor. You have a good day. All right.
Yeah, you too. Are you still wanting to meet for office hours?
No, I'm gonna work on them on my own, and then maybe Monday I'll take some of your time.
Sounds good.
All right, Professor. Have a good day.